A very good afternoon to all the participants. So our today's speaker, Professor S.K. Tomar sir, is about to join in next 2 or 3 minutes. And I would also like to add that yesterday only I have shared the assignment and lecture notes which the Professor Kapil Sharma sir has shared with us. So now each and every one of you has this assignment as well as this lecture notes. So you may go through it. And as Professor Kapil Sharma sir has already told all of us that in case of any discussion or any query, they may contact sir, or we can have a discussion about this in the tutorial also. And these lecture notes are about the initial value problems.
What about the assignments, ma'am?
Assignments you people can do, and you may send your soft copy of the assignment via on the same email ID.
In case we're not able to do some of the assignments, will there be any tutorials?
We can discuss. And if you want to have some discussion or some query, particularly to be discussed with Professor Kapil Sharma sir, then thing is also possible. Because sir already told us and all the participants also that they can discuss with sir also.
All right, ma'am. Thank you.
Because there must be few in-depth or in detailed queries that can be very much carefully handled by the Professor Kapil Sharma sir only. And I hope you all have filled the Google form also, which has been shared with you all for the preparation of the certificates. Because as you write your name in that particular Google form, the same will reflect in your certificate also. And most importantly, as we have shared this important aspect in the email also, that the attendance for all the sessions will be counted, and then accordingly the certificate will be generated, and the certificate will be sent to each and every participant via email.
Some of us may not have filled the form, but the form is no longer accepting responses.
Okay, I will do it in the other way so that it makes the accept the responses. Then the
Uh,
other will also fill up the form. I hope that will be convenient to you.
yeah, if we can toggle that so that we can fill up the form.
Yeah, sure, I'll do.
But just write the time and date also, last date in that form filling, no?
Right, ma'am. We really hope that you all have enjoyed all the sessions in a very in-depth manner, because each and every expert has explained the concept in very detail, and all the lectures are on the different topics. Because in differential equations, solving part is important, as well as the uh, understanding of the solving part, right? That is related to the theory behind the solution. That is really important to understand, because that theory is going to connect with the physical process or the physical situation which actually occurs there. There is some technical glitch. That's why. Okay, sir is there. So, very good afternoon, sir.
Hello,
Hello. Very good afternoon, sir.
a very
Good
good
afternoon,
afternoon.
sir.
Am I
Good
audible
afternoon,
now?
sir.
Yes, sir. Perfectly fine, sir.
Yes.
Thank you. Okay, please go ahead.
Yeah, thank you, sir. Thank you very much, sir. A very good afternoon to all the esteemed gathering here. On the behalf of organizing committee, I, Dr. Lakveer Kaur, would express my warmest welcome to all the present here from the different part of the country to the second week of 2 weeks teacher enrichment workshop entitled as Differential Equation and Mathematical Modeling, held at JP Institute of Information Technology, Noida, in collaboration with National Center for Mathematics, a joint center of IIT Bombay and TFIR Mumbai. So first and foremost, I would like to request all the participants to please keep your mic at the mute mode for the smooth functioning of the session. As we all know that differential equations are one of the incredible tools as far as science, engineering, and all real life situations are concerned. Thus, it is practically important for all the scientists and engineers to be able to model physical problems using differential equation and then to solve these equations so that the behavior of the system can be visualized in comprehensive manner. We hope that you all have enjoyed all the previous sessions of this TEW in such a way that you may have explored new understanding about differential equations and mathematical modeling. Moreover, I have firm belief that all the participants are getting in-depth understanding about these concepts, which can be further utilized in teaching as well as in research. So, in continuation of our previous sessions, today we are going to have an expert lecture by Professor S.K. Tomar sir. And we are delighted to share that Professor S.K. Tomar sir has already joined the session. And and it's our proud privilege that Professor S.K. Tomar sir is an integral part of this teacher enrichment workshop. Sir, we are really grateful to you for providing your precious time from the busy schedule, very busy schedule, for this teacher enrichment workshop and investing your sincere efforts for all the participants of this TEW. Professor S.K. Tomar sir is Vice Chancellor, J.C. Bose University of Science and Technology, YMC, Faridabad, and Honorary Director, UGC, HRDC, Dean Student Welfare, Dean Research, Panjab University, Chandigarh. Moreover, he is also former Head Department of Mathematics, Panjab University, Chandigarh. He has worked as Chairperson, Department of Applied Mathematics, Guru Jampeshwar University, Hisar, and established the department during 1995 to 1996 and engaged in various activities of this university in its formative stages. He also worked as a warden, Boys Hostel, Punjab University, Chandigarh, in addition to his teaching and research assignments. He acted as chairperson, Department of Mathematics, Center for Advanced Study in Mathematics, Punjab University, Chandigarh, and coordinator of UGC CAS program of Department of Mathematics, Punjab University, Chandigarh. Actually, list is very large, and I just mentioned here the few. His research interests are applied mathematics, mechanics of continuous media, fluid convections, and numerical methods. And the sir is elected as a fellow of National Academy of Sciences, India, in the year 2017. He is member of International Academy of Physical Sciences, Allahabad. Sir got first prize for best seminar presentation in the 5th SERC School on Advanced Geophysical Fluid Dynamics in the year 1999 at National Geophysical Research Institute, Hyderabad, India. Sir has been elected as Vice President of Madras, India Regional Chapter of Acoustical Society of America. Sir has been awarded with P.L. Bhatnagar Award Lecture of Indian Mathematical Society at 80th Annual Conference of Indian Mathematical Society held at ISM Dhanbad. He is former President of Chandigarh Vigyan Parishad, registered at Chandigarh under Society Registration Act, and he is also advisor of Punjab University Study Center of Research Institute, Governor's nominee on Executive Council of Guru Jampeshwar University of Science and Technology, Hisar. And moreover, in addition to all this, Sir is also member of Academic Council and expert member on the Faculty of Sciences, Kurukshetra University. Sir has been awarded with the Certificate of Outstanding Contribution in Reviewing from the journal, International Journal of Solids and Structures. Sir is also a member of Academic Advisory Council for MOOCs at CEC, New Delhi. He has been nominated as member of Executive Council of Central University at Himachal Pradesh for the period of 3 years, starting from January 10, 2020. Moreover, he is appointed as ex officio member of Academic Advisory Committee of UGC HRDC of GNDU, Amritsar. And there is more appointments and more awards also, but here I just mentioned the few one. So, and Sir has published more than 119 research papers in various reputed journals with high impact factor, and he has more than 33 years of teaching and research experience. He delivered more than 130 keynotes and expert lecture in various international conferences, workshops, short-term courses, etc. in India and abroad. Sir has visited many countries like Switzerland, UK, Canada, Germany, Hungary, China, Spain, many other for their academic and research collaborations. We are really distinguishedly honored that Professor S.K. Tomar sir is one of the expert speakers for this teacher enrichment workshop. With these words, I would like to request Professor S.K. Tomar sir to please start the session.
Thank you, Dr. Lakhvir,
Thank you, sir.
organizers of this teacher enrichment program, dear participants from different parts of the country. First of all, I would like to congratulate the university and the organizers and the Department of Mathematics of JP University, Noida. And I think it is very, very important to organize such programs for the teachers because of certain reasons. Number one, you find opportunity to interact with new buddies who is attending the conferences, and you can have an opportunity to refresh yourself, and that refreshment gives you new direction to ponder upon in your teaching as well as in your research. The topic differential equations and mathematical modeling has very wisely chosen, because these two components, mathematical modeling contains differential equations, particularly in case of where there is change of one variable with respect to other. I have been asked to deliver lectures on the basic concepts of elasticity and elastic waves. And that is my area in which I try to do some modeling, and the research, most of the research is devoted to this area only. To start with, I would like to make some comments which those who have joined this workshop first time, they might be updated that what had happened in the subject in the earlier days and what is going on nowadays. See, Robert Hooke, Hooke's law, everybody might have heard about him, and the simple law that tension is proportional to extension is very, very simple, and everybody at the syllabus of 10th level has very well aware about this Hooke's law. But as far as experimental verification of this law is concerned, Robert Hooke took around 20 years to verify. And this is such a nice law that it is not being used in physics and mathematics, but it is being used in social sciences. Once upon a time, I was asked to attend a conference in social science, and particularly in a subject psychology. And when the student was giving her presentation, he came across two terms: the stress or tension and the resilience. He said that the resilience, that means the power to bear the stress, mental stress, they are proportional to each other. I immediately could picked up that this is the same thing as Hooke's proposed. And I was astonishing that this law was being implemented on the data collected by the questionnaire, and he was showing the results in terms of the resilience and the tension, which we people generally use this word that I am under tension today, or we say that use yoga tricks to remove your tensions and so on. So such a nice law which was proposed by Robert Hooke long back, and maybe around 1670 or so, and he took around 20 years to verify. So certainly this is a fundamental research, and which later was extended to so many areas. But this law was basically given for one-dimensional thing, one-dimensional road. Nowadays, we are using this law for three-dimensional materials. It was Cauchy who basically extended this law for three-dimensional bodies, and the different forms of this law, that means something like the body when it is completely isotropic and homogeneous, the law takes very simple form. The body may be anisotropic, and you can find out the forms of mathematical forms of this law for that bodies also. And this law basically contains three things. One is the component of stress, the component of strain, and the material characteristics. So these three things are basically connected through the Hooke's law, and it is said that if you know the strain and the character and the stress, then you can find out the characteristics of the body, material characteristics of the body. For example, the simplest one is the Young's modulus. So you say that the stress upon strain is the Young's modulus. Similarly, the Poisson ratio can be obtained. So this was just the introduction of Hooke's law. But my topic is to discuss with you is that how the strain can be measured, and the once strain is measured, then you can find out the corresponding strain, the stress at that point. And because I will be using the basic concepts where the component of strains in terms of the displacement are expressed, so that is one of the important point where the mathematical or mathematics starts in explaining different concepts of the theory of elasticity. For your information, the body is said to be rigid when the body is subjected to some external forces and the position of its particles do not alter at all. And you can say that the distance between any two particles of the body that is not altered at all. Such a body is said to be rigid body. Otherwise, the body is said to be elastic body. So in nature, almost every body is elastic body to the small or large extent. When any body, maybe steel or any other material, maybe rock material or man-made manufactured material, if they are being subjected to some external forces, then the relative positions of the particles of the material, they undergo a change and the body is said to be under strain. This is the definition of, and if the external forces are removed completely and the body comes back immediately in its shape and size, then the body is said to possess the property of elasticity. But if the body does not come to the original shape and size immediately, then the body may be called as viscoelastic body. In that case, the strain are functions of time also. So within no time, the body recovers its original shape and size, we say that the body is perfectly elastic. But in nature, no body is perfectly elastic. So as far as the concept of external forces are concerned, there are two main external forces. One is the body force and other is the surface force. The body force is proportional to the volume of the body or mass of the body, because volume can be expressed in terms of mass by the formula or by the characteristic which is called density. And you know that density is equal to mass upon volume. So volume can be said as mass upon density, or the mass can be expressed in terms of volume rho into V. So you can express, or you can define the body force as proportional to the volume of the body or proportional to the mass of the body. So this is the definition of what you call body force. And the surface force are those forces which can act across a surface only. And you see that if there is a surface force, then it would act along the or across a surface only. For example, if you have a cardboard in your hand, and if you put in the direction perpendicular to the direction of blowing air, then you will experience a force, and the air pressure will try to take the cardboard in the direction in which it is blowing, it is flowing. But at the other end, if you take a alpin in your hand and put against the blowing air, then you will hardly feel any force which is exerted by the air, and hence you can prove that the surface force or the air do not have the quantity or quality of a point force, but it is a surface force. So with these simple and lucid definitions, I would like to start my lecture by sharing my slides on how to measure the components of strain. So here I'm going share. This is share, and okay, window, and here I go, and this is sharing. Is it visible to all of you?
Yes, sir.
All right.
Yes, sir.
Okay, so let me explain the plane deformation, and then I'll go to the concept what you call the Cauchy's concept of extending the one-dimensional law of Hooke's to the three-dimension. But anyway, can I give you? Yes, it's okay. So here, what I'm considering is a plane, and the plane is PQRS. This you can see, PQRS. Now here you will see how the differential equations are being evolved from the basic concept of mathematics in a real world problems. So try to understand what I'm doing and how mathematics is useful for finding out the different measures of the strain when the body is under the subject of some external forces. So here I am taking that there is a body, and you know body is nothing but is considered as something, a collection of particles, and collection of particles in such a way that there is no gap between the two adjacent particles of the body. So this is the physical hypothesis I'm telling with you. I am sharing with you that if the distance between the two adjacent particles of a material body is 0, then we say that the body is a continuum body or a continuous body. Mathematically, if you want to define it, then you say that the body is a finite body. I'm talking about finite body. Here, a body is nothing but is a matter which can occupy some space and volume and has some surface. So what I want to say, that if you have a finite volume, and if you say that there exists a one-one function between the geometrical points within the finite volume and the points of the space, then you will see that because there are infinite points in space, and these infinite points are being mapped one-to-one within a finite region of which I am calling a body. So you can see that there would be no gap between the adjacent particles of the body. And why this requirement is necessary for me? Because I want to apply mathematics, and in mathematics, particularly in calculus where we talk about rate of change of one variable with respect to other. So it is basically dy by dx, and dy by dx is nothing but it is limiting of delta y upon delta x when delta x approaches to 0. So this means that dy by dx involve the definition of limit, and limit of a function would always exist, will always exist if the function is continuous. So if I want to make delta y by delta x a continuous function, then the limit would exist, and I would be sure enough, I would be 100% trusted, or you can say without any doubt, I can use that the limit of such a function would exist. To bring the continuity in these functions, I need to assume that the body is continuum body or continuous body. And therefore, for any of the mathematical modeling, particularly in solid or fluid mechanics, the continuum hypothesis is very, very important. Okay, so there is a body, maybe finite or infinite, and I'm taking a cross section of the body, which I am taking PQRS. So the area between this PQRS is completely filled with the material body. So the particles are there at every point of this region PQRS. All right. Now, because it is, I have taken PQ as of length delta x or dx, and PS as of length delta y or dy. So this part of the body, which is a plane, is there before you, and when the body is without strain, that means the body is unstrained. Now, as I said, if the body is subjected to some external forces, okay, and I said by definition that whenever the body is subjected to some external forces, the particles of the body would undergo a change. Therefore, the particle which was placed at the point P, at the point Q, at the point R, at the point S, they will change. And after changing, they will occupy the position. P will take the position P dash, Q will take the position Q dash, S will take the position S dash, you can see here, and R is taking the position R dash. Now, with respect to any Cartesian coordinate system, which I have defined here with OX and OY, because I am talking about the plane deformation, so there is no need to take OZ. Only these two axes would serve my purpose. So I am taking this PQRS in such a way that the PQ is parallel to x-axis and PS is parallel to y-axis, and the particles have gone changed as P dash, Q dash, R dash, and S dash when the body is under strain. So I can define that if P point has the coordinate as x comma y, then P dash would have the position as x dash and y dash. Similarly, the point Q would have the position x plus dx comma y, but it has now changed to Q dash. So I don't know. X plus x dash becomes, suppose, x dash plus dx dash, and y, which was the y ordinate of the point Q, has now becomes y dash plus dy dash. So this is how the notations has been taken. Anyway, similarly, S and S dash can be defined. So here, I did not particularly shown S dash, Q dash, but anyway, that would not make me any trouble. So here you can see the position of the point P is X and Y, and the position of the point Q is X plus dx, and this is Y. So I know the position of P and the position of Q. What is my aim? What is my aim? My aim is basically that if this was the segment PQ in the undeformed state of the body, how much it has been changed in position, that means in length, or and in orientation. Orientation means when in the unstrained position of the body, the segment PQ was parallel to x-axis. After the deformation, when the particles P has gone to P dash, the particle Q has gone to Q dash, how much P dash Q dash is different from PQ, and because this was earlier parallel, how much this angle has been changed from the parallel x-axis to the now the strained positions of P dash Q. This is my aim. Now you see that you can construct such a triangle by just drawing a line parallel to x-axis, which is P dash M dash, drawing a line parallel to y-axis, which is equal to Q dash, and perpendicular to x-axis, that is Q dash M. And here you can see that this becomes a right angle triangle. So if you want to find out P dash Q dash, then P dash Q dash is nothing but P dash M dash whole square plus Q dash M dash whole square root. And then you can find out P dash Q dash. Once P dash Q dash is obtained, you can find out, you know what was PQ. So you can subtract P dash Q dash minus PQ to find out change in length. And how can you find out gamma 1 and gamma 2? It's simple. In the unstrained position, these two arms of these two sides of the rectangle were 90 degree at 90 degree, but after that they are different. So how much this had changed is important. Just a minute, let me put it in DND. Okay, so this is my aim, to find out gamma 1, gamma 2 and the change in length PQ that can be obtained by P dash Q dash minus PQ. Anyway, let me start doing the things. Now P has changed to P dash. Okay, now here is the important thing. What is that important? You see, you are saying that P has gone to P dash. So how much horizontal distance has been displaced? U. And how much vertical distance has been taken place by P dash is V. So U and V are the two distances which are horizontal and vertical distances and were earlier from the origin were at X and Y. So when you want to find out U, or you want to just look at the distance U and the distance V, then one thing is very clear. Whenever a particle is changing its position, then the new position, the distance of the new position, or the change of position of the new position of the particle will depend upon the original position. And how it is true? See, you have a very good example here. Suppose a number of students are there inside a room, okay, and those students are standing and side by side. They don't have much gap in between them. And if someone put some force from outside through the gate, then you see that those who were standing near the gate, they will be displaced more than those students who are away from the gate. So this means that the position of displacement of a particle depends upon its original position, and therefore the displacement is a function of the original position of the particle. So if you want to see the displacement of P dash, that means U and V, they must be the function of the original position of the particle P. And this is what I did here, that U is a function of x comma y and V is a function of phi of x comma y. Certainly I have to take different functions because the distances are different. The vertical or displacement, horizontal displacement and vertical displacements are different. Therefore U is a function of x comma y and V is a function of phi x comma y. Certainly f and phi are continuous functions of x and y. This is where I am incorporating mathematics. Okay, now let u dash v dash be the displacement of q and q dash. I considered the displacement of p and p dash and defined the displacement u and v as function of f of x comma y and function of phi of x comma y. Now I want to talk the similar thing about q and q dash. So q went to q dash, and suppose q displaced horizontally at u dash and this q changes or displaced vertically through v dash. So certain relation should be, certain functional would be between u dash and v dash and the position of the particle q, and this is what I explained here. So u dash is equal to f of x comma dx, x plus dx, because it was the original position of the point q comma y, and v dash is equal to phi dash x plus dx comma y. So I think this is I'm just moving slowly so that I can show some mathematical concept coming into your modeling here, and how I am taking them continuity, or which is a requirement for me. And you see in the next step that here u dash has been expressed in terms of the or by means of Taylor series expansion. And how come it is there? Because I assumed that f is continuous and possesses several derivatives, and therefore u dash can be written as f of x comma y plus curly f by curly x dx plus order of dx whole square. What is the purpose that I am taking order of dx square or higher terms are considering here? The purpose is that when the external forces are being applied on the body, then the positions of the particle are changing their relative positions, but the change is small, and that change is small and in such a way that the original rectangle which was taken in the form of dx and dy, dx and dy are also small, and therefore order of dx square. I'm writing because I'll assume that dx was taken to be small and these terms can be neglected, but somehow these are neglected and you are left with that u dash is equal to u plus curly u by curly x dx, and I'm taking this is equal to mn. Why mn? You can see it. U dash is from this to this, and you see this is nothing but mn or nm. आप इसको mn कहें या nm कहें, one and the same thing. So u dash is equal to, so you got the expression of nm. Okay, similarly I applied v dash, और v dash में भी वही formula apply किया Taylor series वाला, and then you got that the expression of v dash comes out to be this. And what about v dash? We can check. V dash is equal to this one, and which is equal to q dash l dash, and I have written it as q dash l dash. Yes. Okay. Now what about p dash q dash? I was talking about p dash q dash in this rectangle, sorry, at right angle triangle. P dash q dash is nothing but p dash m dash whole square plus q dash m dash whole square and then square root. So ultimately I would be in need of p dash m dash, and I would be in need of q dash m dash. But here from this figure, p dash q dash is nothing but lm. And how can you find out lm? Lm I would like to find out as om minus ol, and similarly q dash m dash can be obtained as mq dash minus mm dash. So these are the simple things from the geometry I am putting before you, and you can see that the same formula have been used here. So p dash q dash is equal to the side square, sum of the side square, square root. As I said, q dash m dash is nothing but q dash l dash minus m dash l dash. And because they have already been evaluated, so q dash l dash is equal to v plus curly v by curly x dx, and m dash l dash is equal to v. You can see m dash l dash is equal to v. M dash L dash is nothing but this P dash K, which is equal to V. So therefore, I put the same thing. And you see, you have got Q dash M dash is equal to curly V by curly X dx. Similarly, I can find out P dash M dash. So P dash M dash, once we can see it here. This is P dash M dash. P dash M dash is nothing but LM, and LM is nothing but LN plus NM. LM NM is U dash. U dash, the value of U dash, I know what is that. And what about LN? LN can be obtained ON minus OL. So all these formulae have been used here. This is P dash N dash is equal to Ln. Ln can be written as On minus OL, and Nm N dash M dash is equal to Nm, and I have put every value. On was x plus dx, OL was x plus u, and which has been become minus x minus u, plus Nm is equal to u plus curly u by curly x dx. So if you see, this comes out to be like this. Now I have two things, P dash M dash and Q dash M dash, and I put it here in the formula of P dash Q dash. And here I expressed this one. 1 square plus curly u by curly x square plus twice into curly u by curly x dx would certainly come out because the square root is there, and dx square can be taken outside, and curly v by curly x, that means this part is also having dx. So dx square would come out, and from the square root sign it is dx. So this is the formula. Now here is the use of the approximation, and that approximation is due to the application point of view. You are saying that right, curly u by curly x and curly v by curly x, they are the small quantities, and their squares would be much smaller, and they are worth negligible. Therefore, I have cancelled out this, and I would be left with 1 plus twice curly u by curly x, right? And raised to the power 1 by 2. So when you apply binomial theorem, it is approximately 1 plus that 2 will get out with this 1 by 2, and you will be left with 1 plus curly u by curly x dx. So this is how the approximations has been used, and you got the approximate length of the segment PQ after deformation as P dash Q dash, which comes out to be this. Now my aim is EXX. I am defining the one component, or the ratio of change in length divided by original length. So this EXX would help me a lot, which is nothing. How do you find out change in length? P dash Q dash minus PQ. And what was the original length? PQ. So I did the same thing, and I obtained curly EXX is equal to curly U by curly X. This is called elongation along the x-axis. If I call EYY, it would be elongation along y-axis. And you can see that the measurement in terms of the change in length divided by original length has been obtained mathematically, and it is equal to curly u by curly x. Next point was how much the angle has been changed. So gamma 1 is the angle between p dash q dash and the x-axis. Yes. So you can apply tangent gamma 1, which is equal to q dash m dash divided by p dash m dash. You have already obtained q dash m dash. You have already obtained p dash m dash, and this is how this comes out to be. Dx will get cancelled as it is non-zero, and you see that you can take 1 plus curly u by curly x to the numerator with the power -1, and if you multiply after binomial theorem, you will see that whatever we are left with, gamma 1 is equal to curly v by curly x. This is simple. I don't think there is any problem. It would be equal to curly v by curly x into 1 minus curly u by curly x. Dx will get cancelled, and then you multiply. What you will get is curly v by curly x minus curly v by curly x into curly u by curly x. But you are saying that the powers of curly u by curly x or curly v by curly x, they are so small that their higher powers and their products are negligible small, and therefore wherever you got the product of these two, that is gone, and you are left with gamma 1 is curly v by curly x. Now the same thing has to do with s to s dash. It was done for p to p dash. So s to s dash is similar. You can obtain the elongation along y-axis is curly v by curly y, and the change in length of the segment from y-axis is gamma 2, is this change in angle, which is equal to curly u by curly y. And these two will help us like this. I'll define exy. Twice of exy is gamma 1 plus gamma 2. And here, how did you consider gamma 1? You said that the change from the original to the deformed is small, and therefore tangent gamma 1 is approximately gamma 1, and therefore gamma 1 is curly v by curly x. Similarly, you obtained gamma 2, and you said that gamma 2 is small, and it is tangent gamma 2 is approximately gamma 2. So this is how exy has been taken. This is intentionally done, twice of exy, because this 2 helps us to put all the components in some compact form. But if you don't take 2, no, it would not affect any of the calculation or any of the mechanical behavior. It is just for the convenience. Some people, some books, they take it 2 and some do not, but it doesn't matter. But anyway, when you take twice of exy is gamma 1 plus gamma 2, the value of gamma 1 and gamma 2 are approximately curly v by curly x plus curly u by curly y, and therefore exy can be put in the form of 1 by 2 curly u by curly x plus curly v by curly x. Okay, and these exx's, eyy, they are called normal strains, while exy is called the shear strain. If gamma 1 and gamma 2 is equal, then the deformation is known as pure shear. But if gamma 1 is equal to 0, then the deformation is known as simple shear parallel to x-axis. So this is how you can find out for a 3-dimensional body that the Eij is equal to half of ui comma j plus uj comma I. So here I tried to put the relation Eij. These Eij are called the component of strain. So for 3-dimensional bodies, if I and j varies from 1 to 3 or x, y, z, then all the components of the component of strain can be obtained in terms of the displacements, where ux, uy, uz would be the displacement along x-axis, y-axis, and z-axis, and comma denotes the derivative. And therefore, the three things exx, eyy, ezz, that means the elongation along x-axis, along y-axis, along z-axis, if you sum up, then it comes out to be curly u by curly x, curly v by curly y, curly w by curly z, and How come these VW are appearing? Because you have this formula. It is just a notation. Ux is taken as U, Uy is taken as V, and Uw is taken, Z is taken as W. And therefore, it comes out to be interesting formula del dot U, a vector. And U vector has component U, V, W. And therefore, this is called dilatation. This is called dilatation. It is an important term in the theory of elasticity. Okay, so I started from two-dimensional thing and extended the things to three-dimensional. Here, one thing I want to tell you, in many of the problems, whether you go in physics or in chemistry or in biology or in any other fields, most of the time it is the only two-dimensional problem which are taken because of the simplicity and the reliability. For example, if in biosciences, if they want to find out what is the structure of the stem of a plant, what they do, they take a cross section of the stem and put it under the microscope, and they analyze that how the structure is there, and they declare that the stem structure of this plant is this much. And so in that case, the cross section is nothing but is a plane thing. So here I am also taking the plane, but I'm assuming that the all in the z direction, the things are same, and therefore this is very useful. If you go to some hospital and you want to know that what about some extra things, or what you call something abnormal is coming out from the body, then they want to take a cross section of that wound or that extra things, and then they put it under the microscope to know that whether it is some dangerous thing or it is some ordinary dead skin or whatever it is. So this is very common. Many of the times the two-dimensional things are being dealt in science, and that too because it gives you the less complexity and more simplicity to analyze the things, and the results are more reliable. Anyway, next concept is the stress concept. Here again I am telling you some important things which are may not be in the books, but you will realize that this is how the mathematics is playing important role. Okay, Lakveer, are the participants are taking interest? I don't know how much they are getting. I'm not sure, but I'm trying my best to put.
Yes, sir, definitely they are getting it.
Okay.
Right, sir.
Stress is very important concept. As I was speaking that as a common word, we use "I'm under stress today." That means I'm in tension. Or we advise the people, don't take tension, don't be stressed. So the concept is same, but we are using the same term in different context. So here in elasticity, the stress is basically when the particles, here it would be more appealing to you how the things are taking place and how we are going to define them. Consider in your mind, just imagine in your mind that there is a body, and the body contains number of particles, of course infinite number of particles. Okay, when the body is subjected to some external forces, what happens? You simply say that the position of the particles will change. Yes, that is true. But when the external forces are completely removed, why the particles are coming back to their original position? What is the need? Yes, that is also very good to think of. What is actually happening? When you are assuming that there is a body, how did the body came into that form? The body could have come to a form occupying space and volume because of the interaction of two particles, or because of the intermolecular forces in between the particles. So it means that the particles are packed and they are in bonding situation because the adjacent particles are having some bonding, and that bonding in physics is called intermolecular forces. If you want to apply an external force on the body, and if the particle are changing their position, actually they are resisting to move. Why they are resisting to move? Because the intermolecular forces are keeping them in contact, keeping them in that situation. That means intermolecular forces are asking them to keep intact, don't go away. But when you are applying external forces, the external forces are more than the intermolecular forces, and the particles are forced to move, are forced to change their position. That means still their tendency is to keep intact, but because the external pressure is so, they are forced to change their position. But during this process of forced position, their resistance is there, and because every particle is occupying or is carrying a resistance, and they are in the opportunity that as and when the external forces are removed, due to that associated resistance force, they come back to their original position. This resistance of the particles not to move from their original position but have been moved because of the forced amount of the force out by the external agencies, they are much higher than their intermolecular forces. So this type of resistance force, or the force which every particle is associated with to resist the motion of their own motion to change their position, is basically the stress. So that is the physics which I was explaining. Now I come to mathematics. You consider a body, take a particle O inside the body. Okay. How many planes can be passed through this point O? Infinite number of planes can be passed. If you want to take a plane passing through the point O, you need to define its normal, its orientation. And that's why n is important. So you take a plane passing through O whose normal is n. That means normal to the plane is n, vector n. Okay. Now that plane would divide the body into two parts. Suppose the left part, particles of the left part are designated by the plus, 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 plus. And the particles on the right of the plane are designated by minus, 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 minus. Okay. This was in unstrained position. The particle, the whole body is being subjected to some external forces. What will happen? All the plus particles they will be changing their relative positions, of course. So it means that every particle will be associated with some force, and that is force of resistance. वो पार्टिकल नहीं जाना चाहते, लेकिन ये पार्टिकल क्योंकि एक्सटर्नल फोर्स ज्यादा है तो अपनी पोजीशन को चेंज करेंगे और अपने साथ वही टेंशन वाली फोर्स जो फोर्स ऑफ रेजिस्टेंस है हर एक के साथ जुड़ी होगी। अब क्या है कि ये पार्टिकल्स दे आर इन कंटिन्यूअस फॉर्म, गैप नहीं है। तो इफ यू लुक एट दिस सरफेस which you considered passing through the point O, and the normal to the plane is defining the orientation of this plane. So every particle of this plane would be associated with a force F, F1, F2, F3, F2, right? Now you forget everything and look at a theorem. What is that theorem? Theorem says if a body is subjected to number of forces, then this system of forces can be reduced to a single force F along with a couple G acting at an arbitrary point O. ये एक स्टैटिक्स में थ्योरम है कि अगर एक बॉडी के ऊपर नंबर ऑफ फोर्सेस एक्ट कर रहे हैं तो these system of forces can be reduced to a single force F acting at an arbitrary point O along with a couple G. ये बड़ी सिंपल सी थ्योरम है and you can trace out. And the same situation is here. If you are saying that every particle on the plane is subjected to some force, so therefore you have a system of forces, and what happens? All this system of forces can be reduced to a single force F along with a couple G. तो लेफ्ट साइड के पार्टिकल राइट साइड के पार्टिकल्स के ऊपर फोर्स लगा रहे हैं और वो फोर्स उसी फोर्स के बराबर है जो इनके साथ एसोसिएटेड है रेजिस्टेंस फोर्स। तो इससे बनता क्या है? यहां से आपकी डेफिनेशन आती है you can measure this force per unit area by saying that if F is the resultant force F, if F is the resultant force and A is the area of the plane, then you can find out F upon A. And if you take the limit in such a way that you can reduce the surface area to 0 but containing the point A, O point contain कर लीजिए, एक सिंगल पॉइंट कंटेन करो और इसका एरिया जो है वो रिड्यूस कर दो उस पॉइंट पर। तो व्हाट हैपेंस? यू विल हैव द डेफिनेशन लिमिट एरिया अप्रोचेस टू 0 F अपॉन A एंड दिस लिमिट इफ नॉन जीरो। अब कैसे नॉन जीरो होगी? बिकॉज F कंटिन्यूअस फंक्शन है। क्यों कंटिन्यूअस फंक्शन है? बिकॉज पार्टिकल के ऊपर F1, F2, F3, F4 वो सब पार्टिकल कंटिन्यूम हाइपोथेसिस में फोर्स कंटिन्यूम है और उनके जो रिजल्टेंट फोर्स भी कंटिन्यूअस है, एरिया ए भी कंटिन्यूअस है क्योंकि एवरी पार्टिकल is within this area is under the continuum hypothesis. Therefore F upon A is continuous function and hence the limit of a continuous function exists, and I am assuming that this is not equal to 0. However, I told you that when the system of forces are reducing to a single point acting at an arbitrary point O along with a couple G, तो मेरी assumption क्या है कि G अपॉन A भी कंटिन्यूअस फंक्शन है लेकिन इसकी लिमिट भी एग्जिस्ट करती है बट द लिमिट इज 0. यस, दिस लिमिट मे नॉट बी 0 एंड वी कैन गिव birth to another theory. which I am not talking about that. So my assumption is that the force upon area limiting value of this is not equal to 0. That means exist and non-zero, while the limit of couple over area is 0. Limit exists but is 0. So this I am taking that the limit of this f upon a, because it is non-zero, I am defining by tau xi comma n yxi comma n, because it will change from position to position and depends upon the orientation of the plane passing through the point. क्योंकि मैंने शुरू में कहा कि जिस पॉइंट से आप प्लेन पास करना चाहते हैं उसमें से तो इनफाइनाइट प्लेन पास हो सकते हैं, but you are taking only that plane whose orientation is defined by n. So if you take a different plane, you will find that the stress force will be different. And if you take the different position of the point, and again, if you choose the arbitrary point O instead of O here, it may be here, the stress force will be different. If you consider here the stress force, and therefore this tau is called stress force, and it depends upon the position and the orientation of the plane across which this force is acting, and it is called stress vector. And because you are saying that this it is a stress vector, so stress vector can be resolved into three parts: along x-axis, along y-axis, and along z-axis. और अगर वो stress का component normal to the plane हो जाए, तो then it is called normal stress, and tangent to the plane है तो वो shear stress है. The component of traction acting on the face of a small cube, which is normal to the positive x direction, are defined by, yes, this is true. What you are saying here, tau x1, tau y1, and tau z1. What do you mean? It is something like that. We call tau x1 is tau xy, tau y1 is tau xy, and something wrong. It must be tau xx. It is tau xx, then it is tau xy, and then it is tau xz. So what you are saying, one is corresponding to x, yes, and y and z are x, y, z are components. So actually there is a simple thing to explain to xy. Different books have different interpretation, but here I'm telling you simplest thing. What is that? When you come across the term tau ij, it means it is the jth component of the stress vector acting across a plane to which xi axis is normal. For example, if I say I is x and j is x, so it is the x component of the stress vector acting across a plane to which x axis is normal. It is not easy to define here. Had it been a physical lecture, then I could have considered a model before you, and then I could have told you the exact meaning of tau ij. कुछ लोग इसको ये भी कहते हैं कि it is the ith component of the stress vector acting across a plane to which xj axis is normal, and this is because tau ij is tau ji, because the symmetry, this is immaterial, and you can understand in any one of these ways. And the 9 components of tau ij are given by like this: tau xx, tau xy, tau xz, tau yx, tau yy, tau yz, and tau zx. So you can see that here x is the first component. So, and these second component x, y, z. So x, y, z are the components in x, y, z direction, and tau x, tau y, tau x, tau x, tau x, tau x, they are basically this one. That means the component along the x direction, and the component along the y direction, tau y, tau y, tau y, and then its component along x, y, z direction, and similarly this one. So this is interesting, and if the figure is there, would help me. Yes, this is there, this is there, this is something like this, tau xx. So on this side of this rectangle or square, tau xx, meaning is suppose this is a plane, this is a plane, so x-axis is normal to the plane, and if some stress is acting on this plane, I am saying that this is a plane and some x-axis is some vector is there, then this vector can be decomposed along this. तो प्लेन भी नॉर्मल टू एक्स एक्सिस है, लेकिन उस पे स्ट्रेस वेक्टर की डायरेक्शन डिफरेंट है, तो उस स्ट्रेस को हम रिजॉल्व कर सकते हैं एक्स एक्सिस में. लेकिन अगर यहां देखें तो ये प्लेन डिफरेंट है, इसके परपेंडिकुलर वाई एक्सिस है, तो इस पे जो स्ट्रेस लगी है उसका जो वाई कंपोनेंट होगा दैट इज टो वाई वाई. सो इन द 2 डायमेंशन दीज थिंग्स आर इजी टू अंडरस्टैंड. इसी तरह शेयर स्ट्रेस को आप देख सकते हैं. Okay, so 3D stresses can also be defined like this. Yeah, interesting. You see, here is a plane. Let me explain. This is a plane, this one, and this plane is perpendicular to y-axis. Okay, so y would remain same in 3 components. मतलब ये कि suppose the stress acting across this plane is having this direction, this one. So this is a vector and it can be decomposed along this direction, along x direction and along z direction. But because this plane is perpendicular to y, therefore it is tau y, tau y, tau y, and x direction is along x and y along y and z along z. And this is how you can understand the others. Okay. So a plane on which there are no shear stress is called principal plane, and the corresponding normal stress is called principal stress. This is just a definition. And let tau 1, tau 2, tau 3 be 3 principal strain, यानी कि वो planes जिनके ऊपर shear stress कोई नहीं है, तो उसमें normal stress को हम principal plane कहते हैं, principal stress कहते हैं, and the such a plane is called principal plane. So if tau 1, tau 2, tau 3 are 3 principal stresses, then they are such that tau 1 is greater than tau 2 equal to and tau greater than equal to tau 3. This is basically related to the Mohr circle, and I'm not going into that maximum or minimum of the things, but this relation is already given in the book. And if tau 1, tau 2, tau 3 are equal and equal to minus P, then P is called pressure, and this is known as hydrostatic pressure or hydrostatic state of stress in solids, and but it should be associated with the negative sign. When principal stresses are not equal, then you can find out that P is equal to minus 1 by 3 tau 1 plus tau 2 plus 3. This is simple. आप तीनों को ऐड कर दीजिए, तीनों की वैल्यू माइनस पी है, तो ये बन जाएगा -3p, एंड देयरफॉर tau 1 plus tau 2 plus tau 3 is equal to -3p, and hence p can be. And we can show that अगर tau 1 plus tau 2 plus tau 3 करें तो -3p as I was telling. और अगर tau xx dash, tau yy dash and tau zz dash are the deviatoric normal stresses हैं, so you can find that tau xx dash plus tau yy dash plus tau z dash is 0. And if you say that deviatoric normal stress is 0, some of the deviatoric normal stresses are 0, then it is already conveyed by this formula that there exists the hydrostatic pressure. And you can find out that the hydrostatic pressure P would be equal to 1 by 3 of tau 1 plus tau 2 plus tau 3. So that is mathematical interpretation only. Now, stress-strain relation is the generalized Hooke's law, and I don't need to say much about it because I have already explained. And tau xx is proportional to exx, जैसे मैंने तुम्हें बताया कि ये 1 dimensional के लिए given था, and the constant is the Young's modulus. And according to generalized Hooke's law, each component, this is given by Cauchy. Cauchy said for 3-dimensional bodies, each component of the stress is linear function of the strain components. And this definition says that tau xx, tau yy, tau zz, tau xz can be written in terms of this. And you see that I am assuming that the coefficient matrix is non-singular. If I assume that T is equal to R into E, then we assume that R inverse exists, and R inverse exists only if R is non-singular, and this exists in such a way that R dash R is equal to R inverse R is equal to R inverse is equal to I. So this is merely an assumption, but these assumptions are already verified because of the continuum hypothesis, 1-1 correspondence, and you see that non-zero or value of this matrix, determinant of the matrix, coefficient matrix. For isotropic bodies, I'm not going into the detail of the what you call the generalized Hooke's law for an isotropic material. But somehow, if you apply the symmetry, the plane symmetry, the axis symmetry, and then the three-dimensional plane symmetry, and then finally the symmetric all directions, or isotropy means that if the property of a material is same in all directions from a point, then the body is said to be isotropic material. And the homogeneity of the property means that if the characteristics or the material characteristics of the body are independent of the positions, then the body is said to be homogeneous. So homogeneous isotropic material is nothing but is an isotropic material. And for this, the Hooke's law for three-dimensional bodies given by Cauchy and extended from the Hooke's law is given by tau ij is equal to lambda. This theta, I'm talking this is a delta, but this delta is triangular delta is basically dilatation, and we have already spoken about this dilatation. And delta ij is chronicle delta, and twice mu eij. Eij are nothing but the component of strain tensor. So lambda mu are called Lami's constant. Lambda does not have direct physical meaning, but mu has. Mu is basically the rigidity, and the value or the physical meaning of lambda can be obtained by through certain formulae. For a special state of stress, when tau xx, tau yy, tau zz is equal to minus p, and tau xy, tau yz, and all the shear stresses are 0, and the principal stress is equal to minus p, then you can see that tau xx, tau yy, tau zz, the value can be obtained from this. And you put them is equal to minus 3p, because it is a sum. You can see that we obtain that p upon delta is minus lambda plus twice by 3, 2 by 3 mu, and I'm saying that this is equal to minus k. This k, which is equal to lambda plus 2 by 3 mu, or which is equal to minus p upon this dilatation, is called modulus of compression, or the bulk modulus, which is a very popular term in mathematics or in physics. And you can see that k is equal to minus p upon delta, which is equal to minus p, and this was the dilatation, which was change in volume divided by original volume. And you can see that this is how you can manipulate that k is equal to p upon minus dv by v naught. And this is called an increase in hydrostatic pressure divided by decrease in frictional volume, is called the bulk modulus. So this is a positive quantity always, and is very important for engineers particularly. Okay, now my question next is how to find out the equation of motion. How do you find out the equation of motion is an important thing, or equation of equilibrium. तो क्या करते हैं कि किसी बॉडी में एक क्यूब एलिमेंट ले लेते हैं, और क्यूब एलिमेंट को हम ये सोचते हैं कि भाई इस पे स्ट्रेसेस तो है, लेकिन ये कहीं मूव नहीं हो रहा है, ये इस पोजीशन में है. तो अब हम with the knowledge we had recently, so we can find out the different components acting on this plane, different component of the stress acting on this plane, and so on. So what I'm just taking the components of the stresses along z direction. y और x के मैंने इन्हीं दिए। तो देखिए क्या है इंपॉर्टेंट यहाँ पे, वो सोचने की बात है और फिर आगे चलते हैं। See, I am taking this cubic element. A is a point here, and I am taking x comma y comma z as the coordinate of the point A. Okay, and this A, B, C, D is a plane perpendicular to z axis. All right. So if I want to find out the stress acting on this point along the z direction as tau zz. So the position of this plane is here, x comma y comma z. And what about this? A parallel plane. The position of the parallel plane had changed. It is at some distance above. Therefore, the stress here would be different. And that different, I am talking tau zz1. So if you assume that tau yz is the stress acting on this plane, then the same stress acting on the different plane at a distance would be something different. So it's a notation. Tau yz1 is a notation, so that tau yz is different from this tau yz. But how to find out these one? There is a formula. Let us consider z component of the stresses on each face of the cube, and on the face A, B, C, D, this is the total stress. How did you find out? Yes, I can find out. A, B, C, D. A, B, C, D. What is the area? Area is, this is along say dx, and this is along y say dy. The area of this rectangle is dx dy. And I am taking the point A where the stress is tau zz. If you want to find out the total stress across the plane, so therefore what you have to do, you multiply the stress here multiplied with the area of the plane, and then I'll say this is a average stress. This is a average stress acting at this point. So tau zz defined here as a surface or the stress per unit area now has been obtained as Tzz is the stress, average stress acting across the plane A, B, C, D. And this is how I did. And because tau zz is downward, is against the z axis, so that's why I considered is minus of Tzz dx dy. And so on other surfaces you can find out. And how to do it then? Then tau zz, as I told you, tau zz1 is representing different from tau zz, and therefore it depends upon the position. And what about the position of tau zz1? It is a plane parallel to the lower plane, but at a height dz. So you can see that tau zz at x comma y comma z plus dz. And then again the continuity and the all conditions of the Taylor series expansion are required here, which I am taking granted that they are there. And then you can find out the expression of tau zz1. This is the expression of tau zz1. And similarly, on other planes, you can find out. So, and suppose x comma y comma z, capital X comma y capital Z are the component of body force along Cartesian coordinate axis, then you can apply to find out this equation of motion. You need to have the fundamental principle of mechanics, which is force is equal to mass into acceleration. And this is what I did. The left side is the total force, which would involve the surface force acting on the cube along the z direction plus the body force acting along the z direction. And how did you do it? It is z x y z is per unit mass. I did not wrote it here. I did not write it here, but anyway, it is per unit mass. And to find out the on total mass, you have to multiply it by rho into dv. So this is how the things has been considered. This is the total body force along the z direction. These are the surface forces, because you considered along the z direction only. So you add them, is equal to mass, yes, into acceleration along z direction, which is equal to d2 or curly 2w by curly t square. And then you see that if you solve it, this gives you this type of what we call equation of motion. And if you don't apply the Newton's equation of motion, you say that the things are in equilibrium, then the total force must be equal to 0. And if you put total force along z direction is equal to 0, you will find out the equation of equilibrium. So they are very closely connected, and there is no problem. And that's why I preferred that the equation of motion is better than to explain the equation of equilibrium. So this is how similarly you can do it. Same for the x-axis and y-axis, and another two equations can be obtained, 1, 2, 3. So these are the three equations of motion. And now you have the stress strain relation for isotropic body. You can find out tau xx, tau yy, tau zz, tau xy, tau yz, and tau zx from this relation, and you can put them here in these three equations to obtain. And then these three equations, by multiplying with unit vector I, j, k, and then combining, you will find that this is the equation of motion. Very popular Navier-Stokes equation of motion in solid mechanics in vectorial form. Here this is the del dot del. Actually, this two things are different. Why? This is basically divergence of del dot u. This is dilatation, which is equal to del dot u. So it is just a notation, no problem. And you can use the identity that del cross u is equal to del dot u. So del dot u is the same thing as this one, minus del square u. And if you apply it, you can put the same equation of motion into this form. And these are the equivalent form, two equivalent form of the equation of motion in vector form. So here the some concept arises. There may be a situation when del dot u is equal to 0. So if there is no change in the volume of the body, what happens? You see that the equation of motion reduced to del square u is equal to 1 upon c square curly 2u by curly, which is clearly the equation of form of the equation of motion in u, and c is equal to mu by rho square root. And then we say that there is a wave of distortion, because you said that there is no change in volume, del dot u is equal to 0. And when del cross u is equal to 0, then you see that this happens, del cross u is equal to 0, while del dot u is equal to del square u. From the identity, you can just see this one, this identity. You said this is equal to 0, therefore this is equal to this one. Okay, and you see that the equation of motion reduces to this one. Good. So this is again the form of the equation, wave equation, and you see that it is a wave propagating with speed c, given by lambda plus twice mu by rho square root, and this wave is called the dilatational wave. Why? Because you assume that del cross u is equal to 0, which is basically the distortion or the curl or the change in orientation, and therefore this is dilatational wave. It can be proved that the dilatational wave is a equivoluminal dilatational wave is distortion, is having del cross u is 0, and the equivoluminal wave is having del dot u is equal to 0. So their speed are mu upon rho square root and lambda plus twice mu upon rho square root. And equivoluminal wave is called distortional wave, and dilatational wave is called irrotational wave. And because of these reasons, that there is no. So if del cross u is not 0, means that the rotation can occur. And if del dot u is equal to 0, means that no change in volume. And therefore del dot u is this one. It can be proved that if the wave is longitudinal, then it is a plane dilatational wave. But if it is a transverse wave, then it is a plane distortional wave. And second thing which we can prove is that del square u is equal to 1 upon c square curly 2u by curly t square represents plane wave at a great distance from the source of disturbance, and they are either dilatational or distortional and travel with a speed one or the other with velocity mu by rho square root and lambda plus twice mu by square root. So this is these are very, very basic concept which I am talking about, and they are simple to prove. For example, you want to prove that the longitudinal, if the wave is longitudinal, then it must be dilatational wave. And but if the wave is transverse, then it must be plane distortional wave. For your knowledge, you already know that longitudinal wave is nothing, but it is a wave which propagate in the medium in such a way that the direction of displacement of the particles are in the same direction as the direction of wave propagation, then it is called longitudinal wave. But if the direction of displacement of the particles are perpendicular to the direction of propagation of the wave, it is called a distortional wave. These are very simple, 10th class mein aapne padha hoga. And you see that let the direction of the wave propagation is along the positive direction of x-axis. Let us assume कि x direction में wave particle displace हो रहे हैं at a great distance from the source. If the waves are longitudinal, then all the particles of the medium will also move along the same direction, that is along positive x direction. Let me tell you one thing. See, suppose you are talking about earthquake waves. Earthquake waves are basically the combination of the P wave and S wave. Later I'll tell you what do we mean by P wave and S wave. It is connected with the dilatational and distortional wave. So what happens, suppose somewhere some explosion takes place. तो explosion के आसपास अगर बात करते हैं तो वहां कोई वेव नहीं होती, वो कुछ नहीं है, वो तो haphazard manner है, that is not in a proper form. लेकिन those vibrations which are created from that explosion, when they propagate to large distances, then they constitute some plane waves, and that plane waves are very, very important to study the characteristics of the medium through which they travel. So in many of the times these seismic waves, particularly I'm talking about the earth medium, are very helpful in detection of some valuable materials, maybe water, maybe hydrocarbons, maybe gold, maybe aluminum, or whatever it is. Because when the wave propagates through that medium, the speed of the wave will change and it would be affected, and it would be depend upon the medium property. और अगर गोल्ड की प्रॉपर्टी है तो वो डिफरेंट है, एल्यूमिनियम की प्रॉपर्टी डिफरेंट है, तो उनमें से पास होने वाली वेव्स हैं, उनकी जो स्पीड है वो भी डिफरेंट होगी. अगर वहां पर हाइड्रोकार्बन्स का रिजर्वायर है तो उसमें से पास होने के टाइम भी उसकी जो वेलोसिटी है, उसकी जो स्पीड है वो चेंज हो जाएगी. एंड दैट्स हाउ वी गेस that this type of material can be obtained here. But this is all based on the theory we are learning here. So let u be the displacement of an infinitesimal element in the x direction. Then I'm taking about u displacement. Therefore, I'll take v and w is equal to 0. And u is a function of x and t only. So we see that exx is equal to curly u by curly x is the only non-zero component of the strain, and therefore the dilatation del theta, जिसको delta बोलते हैं, is curly u by curly x only. And second derivative 0 होंगे, और with respect to y, with respect to z 0 होगा, because u is a function of x and t only. And therefore with these values, if you if you insert these assumptions into the three equation of motion, and then if you look at the calculations and the summation and other things, you will see that it happens. और ये हमने प्रूव किया है कि ये तो डायलेटेशनल वेव है, और चूंकि आप चले थे लॉन्गिट्यूडनल वेव से, एंड देयरफॉर इट प्रूव्स दैट the longitudinal waves are nothing but the dilatational wave, और speed भी वही रहती है. And similarly, अगर आप prove करना चाहते हैं कि transverse wave के बारे में, distortional wave and transverse wave, a similar relation can be obtained. But anyway, these are certain things. ये कुछ solution of the equation की बात कर रहे हैं यहाँ पर. This is a one-dimensional equation. We can talk about the solution, and this is in the transform domain, xi and eta domain, and the transformation is x minus c1t and x plus c1t. And you can see this is a D'Alembert solution of the wave equation, and it can be easily explored from the books, and is a simple one. I'm not going into the detail. I'm just putting the things in some calculation form, but you see that the solution gives you in the two forms, f of xi and zeta of b of xi, where f and g are arbitrary functions, and xi and eta are x minus c1t and x plus c1t. And we say that u is equal to f of x minus c1t plus g of x plus c1t are the two wave solutions. And that wave solution represents in this form. जो एक f of x minus c1t है, it represents the wavefront of a wave traveling through a positive direction of x-axis with speed c1. And similarly g of x plus c1t को explain कर लेते हैं. तो ये simple चीजें हैं, इसमें मैं कुछ ज्यादा नहीं बोल रहा हूँ. But mathematics is being used. जैसे यहाँ continuity of the function की बात करके हम v is equal to c1 निकाल लेते हैं, कुछ attenuation और distortion के concept हम introduce करते हैं. But actually my aim is to tell you something which you might be looking for. Just a minute. Yes, some wave propagation. In physics, waves are usually divided into two groups. One is progressive waves and other is stationary wave or standing wave. So seismic waves are also of these two types. One is progressive wave, जिसको P wave भी कहते हैं, और secondary wave या standing wave, उसको S wave भी कहते हैं. So progressive seismic waves are body waves and surface waves. So body waves are longitudinal waves and transverse waves in nature, while surface waves are like Rayleigh waves, Love waves, or Stoneleigh waves. So these waves, surface waves, earthquake waves are basically the surface waves. So particularly they are either Rayleigh waves or Love waves. And I want to find out what about the Rayleigh waves. So दो चीजें मैं explain करूंगा. I have 15 minutes to go. तो ये Rayleigh और Love wave की बात करके मैं अपना topic खत्म करूंगा. So Rayleigh wave basically are first discovered by Rayleigh, Lord Rayleigh, and it is mathematics who could initiate the study of this youngest branch of science, which is called seismology. So seismology was initiated around 1882. Now it is more than maybe around 150 years, but it is giving a lot of inputs from mathematics and physics, and together they have created a lot of models and a lot of information about our planet. So
one quick question.
क्वेश्चन पूछना चाहते हैं आप? बताइए.
यस सर, ये जितने भी वेव्स है सर,
हाँ.
वो इस जो मैथ का मॉडल है del to u by del x square equals c square del to u by, इससे रिप्रेजेंट कर सकते हैं सभी को या अलग अलग करना पड़ता है सर?
बिल्कुल अलग अलग करना पड़ता है.
ओके ठीक है सर. ओके
ठीक है, उसका रीजन है. देखिए मैं वेव्स के बारे में बताऊं. बेसिकली देयर आर टू टाइप ऑफ वेव्स. वन इज मैकेनिकल वेव्स एंड अदर इज नॉन मैकेनिकल वेव्स. But mechanical waves are those waves which can travel through or which need some medium to travel. And there are waves which do not need any medium to travel, like electromagnetic waves. They can travel through the vacuum also. So we are generally talking here about the mechanical waves. Number one. Number two is कि wave equation is basically the disturbance which you are representing in mathematics form. और disturbance जो है वो basically is traveling from one place to another place without changing the medium itself, but it is the transfer of energy from one place to another place. So these things are very important, and I'm speaking and you are listening, and that listening is possible because of certain medium, and that medium is what you call the electronic medium.
Yes, yes.
Right? And this electronic medium, when the wave travels from some reflector, तो वो आपकी इस मीडियम से ट्रेवल करके रिसीवर तक जाती हैं और आपको सुन रही हैं. तो वेव के बिना तो इस दुनिया में कुछ भी नहीं है. अगर एक दूसरे आदमी को हम ना सुन सके, यानी कि अकॉस्टिक वेव ना चले, तो हम किसी को सुन ही नहीं सकते. दूसरा ये है कि जितनी भी हम नॉलेज अर्थ के बारे में आज रखते हैं, कैसे कि अर्थ की जो रेडियस है वो 6,700 किलोमीटर है, जिसमें से अप टू 30 किलोमीटर टू 50 किलोमीटर क्रस्ट है, एंड देन अप टू 200 किलोमीटर मेंटल है, एंड देन रेस्ट ऑफ द मिडल पोर्शन और द सेंट्रल पोर्शन इज द कोर. Now this has not been possible that someone has digged out the total earth. No, this is because of the propagation of body waves inside the earth, and that were observed through some geophones on some observing stations. And it is now we are going towards the more what you call advancement. How can we predict the earthquakes? So that, देखिए, earthquake is such a phenomena which we can never stop because it is a natural phenomena, and number of disturbances are taking place every day. Those who are strong enough and can come up to the earth surface are noticeable. Rest of the things are, देखिए, आप अपनी body ले लीजिए, at some times your some portion of the body vibrates. You realize कि vibration हो रही है, लेकिन वो क्यों हुई, कैसे हुआ, never know. The similar is the earth body. Earth body के अंदर कितनी disturbances हो रही हैं कुछ नहीं पता, but those who appears up to the surface, they are basically noticeable. So thousands of earthquakes takes place daily, but only few can be observed from that. Now, whenever these waves are coming from the focus to the earth surface, they certainly travel different medium, and when you travel, when you measure them, आपको पता चले कि ये P फॉर्म की, S फॉर्म की किस स्पीड से आ रही है, कितनी अटेन्यूएट हो रही है, you can guess about the internal structure of the earth. And that's why today we know a lot of about the crust, mantle, and the core also. Core is such a thing which is at very, very high temperature and is the form of the liquid but harder than the solid. ये सब चीजें बड़ी इंटरेस्टिंग है कि ये कैसे हो सकता है कि उसकी जो नेचर है वो लिक्विड है बट हार्डर देन द सॉलिड. सो इट इज एस्टोनिशिंग, बट दिस इज एट सो हाई टेम्परेचर कि जैसे आपके पास आयरन है, आयरन को अगर आप इफ यू गिव हीट and it can be reduced to some liquid form, so it is certainly in the form of a solid but can be reduced to or can be converted to or can be transformed to liquid form. So that is there because of the high temperature, one reason, but there are some other reason also that the core is still in the liquid form. And it was proved that because of the liquid nature of the core, no S wave can travel. No S wave, secondary wave, because that is a distortional wave, that is a transverse wave, and the fluid property do not support transverse waves. And so these things are very, very important, and the knowledge has been produced so far is very useful for the further research and the further development in the. But anyway, this Rayleigh wave are basically modeled something like on the surface, on the half space. हम क्या करते हैं कि if you consider the earth as a semi-infinite medium, that means there are two medium, one is above the earth and another is below the earth. So if the below the earth is the solid portion and above the earth is nothing but it is air, and you can consider that it is negligible type of thing. So we can call this as, or we can model the earth as free surface. Z is equal to 0 is the earth surface, and the lower surface, lower as a half space. So it is earth elastic half space and the free surface. The free surface means that there is no stress, there is no force acting on the surface. And you see that it has been modeled like this is along x-axis and this is along z-axis. So the component of u is u and w are 0, and the component v is equal to 0. I am assuming that all the quantities which are derivable with respect to y are 0. And these are the boundary conditions, because I am saying that there is no stress, there is no force acting on the body. So all these stresses must vanish, and all these stresses, the plane is perpendicular to z-axis, and therefore z is occurring here. And the component are along the x-axis, y-axis, and z-axis. So you put them equal to 0. These would act as a boundary condition. And these are the situations which have been modeled like this. And these are the functions x, z, and t, because you are not involving y coordinate. And then these are the equation of motion. Good. And because you are assuming w is equal to v is equal to 0, here it must be w. Sorry, it is w, not v. V is already taken 0. So it must be equal to w. So you have considered u and w, sorry. And then you find out first the solution from the equation of motion. And there is a criteria that we express the displacement or vector into some potential functions, which is through the Helmholtz decomposition theorem. And if those who are conversate with this Helmholtz decomposition, they can pick up it very well. And then you can see that these are the equations of motion 1 and 3, which satisfy with C1 and C2. And the Rayleigh wave are basically the combination of the dilatational wave and the transverse wave. So this is a way to prove that the earthquake waves are the combination of the dilatational wave and the transverse waves, or the longitudinal wave and the transverse wave. Then the existence of Rayleigh wave is considered. The simplest form of the potential disturbances phi and psi are considered in the sine and cosine form, and then it is being used in some equations of motion to take the solution in the form of r square and b square. ये थोड़ा सा tricky है, but is interesting. So I don't think I can go ahead. So
Sir.
now I can take some questions.
Right, sir. So any queries from the participant side, please? So you really have explained each and every definition in a very interactive manner and in a very detailed
But
manner.
had it been in a physical mode, then the interest can be inculcated in a better way.
Right,
But
sir.
this way of presenting the things and telling to those who are not conversate with the area, perhaps would find difficult or will be difficult to understand. But anyway, this is what we can do right now. Okay.
Right, sir. But we are privileged that we have attended your lecture offline also in
Yes,
our
sir.
conference, Ramsa.
Good afternoon, sir. Hello, sir.
Yes,
I have a small doubt, sir.
yes, please.
Sir, actually, so when that S wave is acted, that this is like both shear horizontal and shear vertical wave. But we know that S wave is a body wave. So when shear, if the case arises for the shear horizontal wave, but we are telling this is a surface wave. So how is it possible, sir?
Actually, because of some disturbance at your end, I could not get you clearly. See,
Hello.
Sir,
the
sir,
communication.
sir, he is asking that about the splitting of S wave, that is the SV and SH wave, and why SH wave is also termed as the surface wave. I think Tapas
Yes,
is
yes,
Yes, sir.
asking
Yes,
the
sir.
same.
So actually, one thing I can tell you, SH wave cannot travel in a half space. It can travel
Yes.
only if a layer is lying or layer is resting over a half space. It was
Yes.
proved by Love, AEH Love in 1911 that the shear horizontal wave can travel only when a layer of finite thickness is lying over the half space and cannot travel if there is only a single half space and no layering is there. So
Yes.
the crust is basically considered as a layer over the half space, and hence the love wave contribute towards the earthquake waves also.
Yes, sir. Thank you, sir.
Okay.
Any other query? So thank you very much, sir, for sharing your profound knowledge and
Okay.
expertise.
Thank you.
Thank you,
Tomar
sir.
sir, thank you.
And your expertise with all the participants and our faculty members of Department of Mathematics. Once again, sir, we are really paying our sincere gratitude to you for providing your precious time from very busy schedule and investing your sincere efforts for all the participants of this teacher enrichment workshop. Hopefully, we will be able to connect with you in offline mode also very soon.
Thank you. Thank you very much. Thank you
So,
so much.
right.
So I don't know how much the students can or the participants got my material which I conveyed, but it appears to be very difficult to convey the things when the applied mathematics comes into picture and some modeling is there. So, but anyway, those who are already in the field, I think they have refreshed them, and they might have got something new also, which are not given in books.
Right, sir.
Thank you. Okay.
We definitely gain the new insight, or I can say in deep insight about the detailed topic of this session. So I hope all the participants have really explored all the session content and received it in a very elaborate manner. So thanks to all of you. Thanks to Sir, Professor S.K.
Thank you.
Tomar, sir, all the participants of this session, and faculty members of our Department of Mathematics, and most importantly, our head Department of Mathematics, Professor Alka Tripathi ma'am, for her continuous support at each and every step. So thanks to all, and we will again connect tomorrow at 2 p.m. with the same link. So thanks to all of you.
Okay, ji.
Lakveer,
Thank you,
thank you
sir.
so much, sir.
Thank you. Thank you very much. Okay.